And welcome you guys to Mathematical Applications. Today we are going to cover units, rates, and conversions. All right, it's going to be really exciting. I had a lot of fun designing this, and let's get started. So hello, my name is Mr. George. All right, so one thing that I want to get out of the way, you guys can hear me still, right?
Yes.
Yes, I hear you.
So one thing that I really want to get out of the way is that I don't want you guys to be scared to ask questions. All right, ask as many questions as you can. All right, because feeling doubt and not knowing how to approach a problem is part of the learning process, and that's something that we really need to internalize, right? If you have a question, you can raise your hand, you can type something in the chat, and Dula will notify me because he's watching the chat, right? So if you have any questions, any doubts at all about anything, feel free to type it in the chat, ask me, raise your hand, or do anything like that. All right, guys? So I really want this to be a cohesive and learning experience. And we don't want anybody to fall behind. All right? Does that sound good?
Yes.
Yeah.
Please ask questions. All right? This is gonna go pretty fast. So yeah. So today we will learn about units, standard international to metric, rates, which is measuring and scoping change in measurement, and conversions, one thing to another, and extracting values from given sets of values. All right. So first of all, what is a unit? Well, a unit is a named quantity chosen as a standard to represent a value. Now, one thing that I learned from my studies is that units are mostly arbitrary. Can anyone tell me what arbitrary means? Arbitrary. Well, arbitrary means is basically that like it's decided by something, by some unknown force. So for example, I have a ruler right here. Can you guys see the ruler?
Yeah.
Yes, I see the ruler.
ruler, right? So basically 1 inch is this amount, right? And so the reason that this 1 inch is this amount is because somebody somewhere decided that this amount of atoms lined up is going to be 1 inch, right? And that's something that we need to understand because these units are just our interpretation of understanding the world, right? And so these different units that we have, seconds, PSI, all of these things, they're going to be measuring different dimensions. Now, dimensions here isn't like some alternate dimension where you're Spider-Man, right? So dimensions here, they're going to be like different sets of values that represent different things. So for example, length is a dimension. We're going to define length as a type of dimension. Now, how we measure these dimensions is going to be through the meter, the inch, the yard, and multiple different other quantities. Now, these quantities, they relate to one another, right? So a fathom is 6 yards, right? A league is 3 fathoms, right? So all these things, they're just different ways to measure things. And all these different names, they're just different names for certain amount of length. And this is important, right? We need to define these units and these metrics in order to observe the world. So for example, if you say, hey, where is this new restaurant? Where's this new Mexican restaurant that I want to go to? Oh, it's down the block. Well, you don't know how big the block is. You don't know how long the road is. But if you tell them, hey, it's like 100 meters down, 100 meters to the right, it's going to be something completely different. You're going to know, these are just ways to understand the world. So for example, for time, we're going to go off of seconds, hours, weeks, and millennium. Does anyone know how many years are in a millennium? Do you guys know how many years are in a millennium? It's okay to say no. No, I don't know.
Wait, in a what?
Millennium, right here. Can you guys see my cursor? Right here. In a millennium. You guys know how? All right.
Years?
How many?
16.
16. No, it's 1,000 years. It's 1,000 years. All right. So, and then we can move on to volume, which is a liter, an ounce, a quart, or even a centimeter cube, right? And so you're going to think, hey, what the heck? A centimeter is a length value, right? But if you take this length value, right, and then you apply it, and then you multiply it by itself, right, that gives you a square area, right? And then if you multiply that square area by another length value, you're going to get a 3D object. But we're going to get into that later, all right? So we can go to more examples. So more examples of different types of dimensions. They can be temperature, pressure, light, mass, and other completely different things. So for example, temperature, we have different scales, right? So degrees Kelvin, degrees Celsius, and degrees Fahrenheit. Now, who can tell me what scale we use here in the United States? Who can tell me?
The question again?
What scale do we use in the United States for temperature? Kelvin, Celsius, or Fahrenheit?
Fahrenheit.
We
We
use
know there are
Fahrenheit.
degrees.
We use Fahrenheit. It's very good. All right. So yeah. So all these different types. So the rest of the world uses Celsius. We use Fahrenheit. So it's just different ways of measuring the same thing, right? And so pressure, we use atmospheres, pascals, millimeters of mercury. Now the funny thing about millimeters of mercury is that like when you set up a table, a dish of mercury, and like a little tube, the atmosphere pushes down on the mercury and it makes it go up a tube. So that's the scale of millimeters of mercury. That's something really interesting. So for light, it's going to be lumens. So the different amount of light that you receive. So like, for example, when you're on your phone and then you change the brightness, you're changing the amount of lumens that your phone emits, right? So different units for light, they're going to be lumens, lux, candles, and foot candles, which is just a bigger version of a candle, right? And so for mass, now, who can tell me? All right, can Nicholas, I saw you entered. Nicholas, can you tell me the difference between mass and weight? All right, Nicholas. Deep Katudia, you're yeah. Can you tell me the difference between mass and weight?
So weight is like how much an object weighs, like how like the weight, like kilograms, pounds, etc. Mass is like the whole object and like what it is.
Like how much mass, how much material is actually in it, right?
Yeah, right.
That's good. All right. So yeah. So for here we're gonna have mass, pounds, and tons. All right. So other units, they're gonna be newtons. Newtons are for force. Coulombs, which is amperes per second, and ampere is just the amount of electric charge that something has, right? So any questions at all? Are you guys good with this?
I'm good.
Everything,
Yeah, I'm good.
everything's good. All right. So let's be sure to be reacting to these things. Yeah. And so when I release this, I expect you guys to know at least most of these units, right? So here we have SI base units. So these are just the basic units. So SI base units. So what an SI means is standard international. So internationally, these units are used as like a basis, right? So since there's this disparity between the United States and Canada and the rest of the world, the SI units are used universally, right? So yeah, they're used universally. So for time, it's going to be seconds. Length, they're always going to be meter. Kilogram. For electric current, it's going to be an ampere. For thermodynamic temperature, it's going to be a Kelvin. So what thermodynamic temperature means, it's just basically temperature, right? Amount of substance is a mole. You guys will learn about that in chemistry. And luminous intensity. So, and then below it, we have the imperial system, which is a different system, right? So we can see here the scales of measurement. So it goes from inches, feet, yards, chains, furlongs, miles, and these are all just different types of measurement. Up next, we're gonna go over the product rules. So basically, what these are, we have to know these for the for unit conversions and such. So power of a product. So basically, when you multiply A and it's the power of X. So I hope everybody knows what a power is, right? Please, everybody, respond.
Yes, I do know what a power is.
I don't
You
know
guys
what a power is.
Who said that?
Me, Aiden.
Okay, and who else doesn't know what a power is? Does anyone else not know? All right, we're gonna go over this really quick. All right, can you guys see the annotation?
Yes, I see the annotation.
Okay, so all right, so we're gonna say A. We have A, right? And we can set A equal to 2, right? So A equals 2. All right, so let's say we have A, right? And then we want to multiply A by itself. So let's go A times A, right? Oh my God. Okay, so A times A. So what is a quicker way that I could write this, right? So, well, I mean, I guess I could do, well, I guess I could write this out. And let's say I want to multiply A by A again, right? A times A. But a quicker way to write this is we can just put A to the power of 3 because you multiplied A by itself 3 times. Does that make sense, guys?
Yes.
Okay, so you multiply A by itself 3 times. And now since A is equal to 2, right? So basically what that means is that you multiply 2 by itself 3 times, right? So that's going to be 2 times 2. What is 2 times 2, guys? It's going to be 4. So then you multiply 4 by 2, right? That's going to be 8. So basically, A to the power of 3 is equal to 2 to the power of 3, which is equal to 8. All right? So that's basically what a power is. We can use this. You can use the same rule for B. Let's say B. Okay, let's say B times B times B times B. Oh my gosh, I'm writing this with my mouth. Times B. All right. So how many times did I multiply B by itself? Who can tell me?
5.
We multiplied it by 5, right? So the notation would be B to the power of what?
5.
5. It would be 5. Perfect. All right. So that's basically what products are. So basically what this is saying, so power of a product. So if we have A to the power of 3, right? So if we have A to the power of 3, oh my gosh. Okay. So if we have A to the power of 3, A to the power of 3, times A to the power of 4, the answer is going to be this power plus this power, right? So that's, what would that be? Anyone tell me what this would be? It would be A to the power of 7, because this is 3 and this is 4. All right, so it's best exemplified right here. So it's x to the power of 8 times x to the power of 2. And now what is 8 plus 2? Can anyone tell me?
10.
It's 10. So that's why there's 10 right there. So yeah, that's good. So power of a power. So whenever you take a power, A to the power of 2, but then you want to multiply A to the power of 2 by itself 3 times, then you'd multiply 2 by 3. All right, does everybody understand?
Yes.
All right. So the last one that we need to understand is quotient of powers. So for example, let's say we have A power of, let's just use this example, right? So if we have x to the power of 8 divided by x to the power of 2, what that's going to be is going to be 8 minus 2. What is 8 minus 2, guys?
6.
8's 6. So that's why we have 6 right there. All right. So we're going to erase this. Okay, we're going to erase all this. All right. So I hope you guys understand. So let me see. How am I doing on time? All right. All right. Okay. All right. Okay. Everybody's good with that? Just a good
Yes.
quick
Yeah.
thing. All right.
Yeah.
So let's go on. All right. So what this allows us to do is this allows us to understand complex units. So for example, let's say your dog ran 8 yards in your backyard, right? So he ran 8 yards. That is a unit of information. You know your dog ran 8 yards, right? But your dog could have ran 8 yards in 10 minutes. He could have run it in 5 seconds. He could have run it in an hour, right? And you're never going to know if you only know the distance, right? But if you put the distance over the time it took, you can get the average the average speed that he was going, right? So if we have here the distance over the time, you're comparing these two units, right? So distance as in being the dimension of distance and time being the dimension of time. So what you can insert the units for each one of these dimensions. So for example, this is arbitrary. We could use meters and per second, right? And so this is going to be measuring how many meters he went for each second that he ran, right? And so we can short this down to like to the symbols of the units, because each unit has a symbol. And this is just going to be equal to velocity, right? You guys following me here? Everything okay?
Yeah.
Yes.
Understand this? All right.
Yeah.
And then, so let's say we have velocity, right? Let's say you're running alongside your dog, right? You guys are running, but then you see that he's speeding up faster than you. Well, why is that? You guys are both have velocity, but you guys need to know the change in velocity. So, for example, in this situation, the dog would have a greater change in velocity because he's speeding up more than you are, right? And so that's going to be the change of velocity over time, right? So it's going to be the change of distance, right? And you're going to put that over time, right? And so what that's going to look like, right, is going to be the meters per second right here, this unit, and you're going to put it over the time. You're going to put it over twice because the velocity itself is the distance over the time, and then you're going to put that velocity, that ratio, over time itself in order to get acceleration. Well, whenever you divide this by this, it's going to be meters over second squared because you're dividing it twice. So these two multiply into the denominator, right? And that can be acceleration, right? Everybody understand? Any questions?
Yes, I understand.
Everybody understands? Can we all
Yeah.
say we understand? All right. So mass times acceleration. So let's say your dog is he has a mass, right? And he's accelerating. Well, that just basically means this is a more abstract component. You guys are going to learn this in your next class. So mass times acceleration, right? So that is a measurement, right? You can use this measurement. So it's going to be kilograms, or the mass of the dog, times this acceleration unit. And that is equivalent to 1 Newton. Do you guys remember when I talked about the Newton and the unit of force, right? So this is equal, mass times acceleration is equal to 1 Newton, and that its dimension is force, right? And so all of these things, they are using the actual observable quantities, and we're applying them through ratios and things. So this is very useful in determining velocity, and determining acceleration, determining force, and just observing the outside world. All right. So here, what all these things are is basically their rate, their ratios between two different numbers, right? So what is a rate? A rate is a measured quantity or frequency related to another quantity or measure. So that's a lot of words to say. For each one of this, I have one of this, right? So for an example, let's say you guys are out picking at a store, right? So let's say for every 3 apples you buy, you also buy 2 pears. Okay, and that's just something fixed. So let's say another example is basically you're working at, I don't know, McDonald's. This is not true, but for 2 hours you would get $30, right? So every 2 hours you're gonna get $30. You work another 2 hours, you get another $2, right? And so another example is, for example, if you have a mechanical pencil, you use 3 pencil leads for each class. Now ratios can be best exemplified through fractions, right? So an example here, fraction, it's 30 miles per 1 hour. Well, that's going to be equal to 30 miles per hour. If you have 33 newtons over 11 meters squared is basically just the component of area, is going to be equal to 3 pascals. 60 coulombs per every 5 seconds, that's going to be equal to 12 amperes. 7 revolutions per 1 minute is going to be 7 RPM. So all these values down here, they're basically just the representation of the ratio: pascals, amps, RPM. All of these are complex units. They're complex because they relate 2 units to each other. All right, so there are different types of rates. For example, there are part to part. So this is a comparison between 2 parts of a whole, right? So, part. I was supposed to give you guys the power rules drill. All right, so once we're done, please go to your homework and look at the power rules drill and do all those questions in your homework, all right? But let's go back to this part to part. So these are comparisons between 2 parts of a whole, right? So for example, in a recipe, it calls for 2 cups of flour for every 3 cups of milk, right? So whenever you're baking a cake, however big you want it, you're always going to want to maintain the ratio of 3 cups for every 2 flours. So let's say that this amount creates 1 cake, right? And so if you want to make 2 cakes, how many cups of milk are you going to need? Does anyone know?
We need 4. Oh wait, 6 actually. Sorry.
You need 6, yeah, because you're going to double it, right? So if the ratio stays the same, but the part to part, even if you increase the quantity. All right, so part to whole. Notice comparison that shows component in relation to the whole, right? So for example, the best way to say this is in a recipe, 3 spoonfuls of sugar for 15 different ingredients used to make juice, right? So what does that tell us? So out of the 15 different ingredients that you need, or the 15 different measurements that you need to make a cake, or to make a juice, sorry, you're gonna need 3 spoons of sugar. That's basically just what it's saying. So for every amount of juice, you're just gonna need 3 spoons of sugar. All right, so these are more abstract rates. So this type of rate is temporal. So rate, ratio, or frequency that is measured over time. So you're gonna see a lot of these. For example, meters per second is one, heart rate, which is beats per minute, blood flow, liters per minute, and sugar consumption, grams per year. So this is the best exemplification of why we need these units, right? Because they display information that would normally be like outside of our range if we only had one dimension, right? So let's see here. Yeah, so sugar consumption, grams per year. These are just things that measure things over time, right? So dimensionless. Let's go over here. Rate comparing 2 numbers of the same unit. So let's say literacy rate, people who can read versus the whole population. Well, both of these units are going to be people, right? It's going to be people over people. So they cancel out. So it has no unit. You guys can look into this later. We have to move on. So basically, does everybody know what a slope is and how it works? Say if you don't.
I know what it is.
We know what it is. So basically what a slope is basically, so on a graph here, we have a line. And so these are literally rates of change themselves, right? So we're just gonna do a little quick overview. So it's 1 over here. Once it moves 1 over here, it moves 3 up. So that's the rate in and of itself. So the slope here is gonna be 3 over 1. And because these are the same unit, it's gonna be unitless, and that's basically what it's saying, all right? Are we good? Can we move on?
Yeah.
Yes.
All right. So let's go. So how do we use these rates? What is the best application? So these are determining and measuring change of variables in respect to each of the other variables. With temporal change, measure change over time. So basically, what we are saying is that we can use graphs like the one back here to measure these changes in rates. So for example, displacement versus time. So this is a displacement versus time graph. So displacement is on the y-axis, time is on the x-axis. So the slope here is meters per second, which is velocity, right? So the slope here is measuring the velocity. So here we have the displacement. And so approximately the amount of this slope is going to be the velocity given by this object. So over here, can you guys see the interval between 2 and 3? What is the velocity here? Can we tell what the velocity is here on this over here?
1.
Anyone? That's not quite. That's close though. Can anyone tell what the velocity is here?
Is it 1.5?
It's not. No, we're just looking at the the interval between 2 and 3. Can you guys see that?
Yeah.
Okay.
So what the slope is basically the rate of change. So it's basically the incline. The slope is the incline, right? And so here, the incline, there is no incline. So therefore, there is no velocity. You guys understand?
Yes.
Yes, we guys understand. Are we getting this?
Yeah.
All right, that's good. All right, so basically here there is no velocity because the slope is in of itself the velocity. And so once there's no slope, there's no velocity. It's right there. All right, so here's another example. So ratio of accepted yen to $1 over time. So basically the Y value is the ratio or rate. So the Y value itself is the rate. So right here we can see the yen over the dollar, right? And so, but then the yen over the dollar, right? So that's basically just a unitless ratio, right? So what it says here, so 132.7 yen per dollar, right? So what does that tell us about the yen? Okay, anyone, just throw stuff out there. if the ratio here is yen per dollar, and it's 132.7 yen per dollar, what does that tell us?
That like it's a lot.
It's a lot. You need a lot of yen to make $1. That's basically what this is saying. And then you can see it over time to see how much the worth of the actual yen is in comparison to the dollar. So here it's at its lowest. So basically, here you need 76.9 yen to make $1, which is pretty good in economic terms. So do we all understand this? It's okay if you don't, if you need some more clarification.
Yes, I understand.
Understand.
we
Yeah, I
good?
understand.
Are we good on this? All right, good.
Yes.
So, percentages. So this is another type of rate. It's a dimensionless mathematical ratio indicating a value per 100. So basically what this is saying is to yield a percentage, we can divide the part from the whole and multiply by 100. So for example, if we have 200 fruits, right, and 80 of them are pineapples, right, we can reduce this fraction, we can divide it, and it's going to give us 40%. So 40% of all the fruits are pineapples. Here's an example. If 18 out of 30 people in your class were boys, then 60% of your class are boys, right? Because we have here 18 out of 30. So this is a part to whole ratio. Percentages are part to whole ratios because you're taking this small component and you're putting this into a larger part, right? So if you have 18 out of 30 people is the whole, right? Because you have 30 people in your class and there's 18 are the boys. So that's the part, right? So then we divide it over here. We set up this ratio and then we divide it and it gives us 0.6, and then we multiply it by 100, which is going to give us 60, which is why 60% of the people are that. So let's say here, if I'm gonna go a little bit over time, if that's okay. We need to get through a lot of this, and the introduction was a little long. This is a long class, so I'm gonna go a little bit over. If that's okay. So if a hoodie costs $3.99 one day and $16.99 the next, that means its price increased by 21.4%. Why? All right. So first of all, we're going to look at the difference between these two prices, right? So what it's asking for, it's the percent increase, right? So it's 16.99 to 13.99. The difference between these two prices is going to be $3, right? And so we take the $3 from the original price, right? Because if it increases, that means that we're taking it from the original price, and it goes up to $16.99. So we're going to take the $3, we're going to divide it by 13.99. That's going to give us 0.214. And we'll multiply it by 100, and that's going to give us 21.4%. Do we understand?
Yes.
We understand? It's okay if you don't. You guys don't have to like say yes just to like keep the class going. If you really have any questions, like that's okay. If you don't understand it, if it's really just not like blocking in the brain, that's okay, because it's part of the learning process. So do we all understand this? Are we all good on this?
Yeah.
We hesitated a little bit. Is that just are we good?
Yes, we are good.
All right. Perfect. All right. So there are a bunch of these questions in your assignment. So please, I'm gonna ask you guys, please don't chat GPT them. Please try to do them. This is for your own growth. All right. It doesn't take anything out of your time. And if you need any help, you can message me. We're gonna set up a group meeting and stuff, and you can message me if you guys need any help with your homework. All right. So here, I'm not gonna go into this a lot. This is just for fractions. We're just gonna look at this. So these are the fraction thingies. If you have a over b and you divide it by c over d, basically you're just gonna split this one and then multiply a over b. So you're just gonna multiply a over d and b times c. This is pretty abstract, right? I'm not gonna go over this. So if it's a over b times c over d, what you're gonna do is you're gonna multiply a times c over b times d, right? Do we all know this? Do we all understand this?
Yes.
All right, I'm not gonna go over this.
Yes.
We need to save time. All right, so all right, applications of rates. So if we use factor analysis, we can determine values from constant rates. So here are some very important application questions. All right, So if we have a car traveling at a constant speed of 50 miles per hour and it drove for 3 hours, how many miles did it travel, right? So does anyone have any idea on how to approach this situation? Any idea? Or any notes that you guys want to do or say on the car? You guys have any suggestions on how to solve this? I'll give you all a little bit of time to think. Any idea? You guys can say no. That's what you guys need to say.
I don't think I know how to do it.
All right. So let's say we have a car traveling at a constant speed of 50 miles per hour and it drove for 3 hours, right? So what we can do basically is we can just set this up as a ratio, right? Like those questions about the fractions that we said earlier. So 50 miles per 1 hour. So basically do you guys remember how the ratios were just fractions, right? So 50 miles over 1 hour times 3 hours over 1. Now, why are we doing this? So basically, we want to set up the equation so that what value do we want to figure out here in this problem? Anyone tell me?
How many miles that it can travel?
How many miles it can travel, right? But what we have here is a value that gives us the miles per hour and the hours. So what we want to do is that we want to multiply these factors out so that we eliminate the hours, right? Because if you put here, let me draw something. Annotate. So if we put, I'm gonna move this. So if you guys can see this, so if we put x times a over b, right, times, all right, then we're gonna multiply this by x times b over a, right? So what does this do? So whenever we multiply this by this, these two values are going to multiply by each other. But then here, there's going to be an a on the top, and then there's going to be an a on the bottom, right? And so whenever you divide a fraction by itself, what is it? If you divide 2 by 2, what is 2 divided by 2?
1.
It's 1, right? So then that means that this just eliminates. If it's 1, then it's canceled out, right? So we can cancel out these, and then also as well, b here is gonna cancel out because there's 1 on the denominator, right? So all we're gonna be left with is x to the power of 2, right? So we want to apply the same logic to the units, right? So since we want to know how many miles we drove, we need to cancel out the hours in order to extract that information, right? So we can set up this ratio. It's going to be 3 miles per 1 hour times 3 hours, right? And we put this over 1 just to make it a little simpler on us. So here, let me exit out of this. So we're going to want to multiply these things, right? It's going to be 50 miles per times 3 hours over 1 hour. So that's basically what this is equal to. And then so since 1 hour and this 3 hours, they're going to cancel out, right? So then that leaves us with 50 miles times 3. And so then the final answer is going to be 150 miles because these two units canceled out and all that we were left with was this actual value that it tells us. So it's going to be 50 miles times 3. Now, if you think about it, right, if he drives 50 miles in 1 hour and he drives for 3 hours, it's just going to be 50 times 3. But this is kind of like the qualitative analysis that we need to use and that we need to impose, right? So does everybody understand?
Yes, I understand.
Yeah.
Am I making sense? All right. So I'm going to let you guys figure this one out. If a planet does 3 revolutions around its sun for every 2 Earth years, if a planet that does 3 revolutions around its sun for every 2 Earth years has completed 17 revolutions, how many Earth years have passed? So what this is basically saying is that it's 3 revolutions, so 3 revolutions around the sun for every 2 Earth years. So if 2 years pass here, that means that 3 years have passed on that planet, right? And if it has completed 17 revolutions, how many Earth years have passed here? Do we understand the question?
Yeah.
Yes.
All right, so how would we set it up? So I would suggest you look at here, right? So this is a given ratio, and then we multiply it by the singular dimension. So how would we set this up? How would we set this up? Anyone have any idea? Any suggestions? Any suggestions?
I would put 3 revolutions, like as a fraction, for the numerator, and
Mm-hmm.
2 below for the denominator.
Okay.
And I would put a X sign, and for that the other one it's gonna be 17 over 1, I'm guessing.
Yes. Very good. Very good. That's exact. It depends. See, now the thing here is that we always want to have the same unit on the opposite sides, because remember, we always want to cancel what we don't need, right? Do you guys understand? We always want to cancel out what we don't need. So if we do 3 revolutions for every 2 years, right? If we put the 17 on top, and that means that when we multiply it, it's going to be revolution squared, and that's the unit that we don't want, right? So it's going to be 3 revolutions for every 2 years, and we're going to put the 17 on the denominator, because we always want it on the opposite side. If one unit is on the numerator, we want the same unit to be on the denominator, because we want them to cancel out, like we said. All right. So 17, 3 revolutions times 1 over the 17. So the 1 is just a placeholder. It's just to ensure it that it makes sense. All right. So what this equals to is going to be, we can do this algebraically. Yeah, so it's going to be times 2 years. So since we have this on the denominator, we can multiply this by times 2 years. Yeah. So this is all going to equal to 3 over 34 years, because 2 years times 17, they are both on the denominator, right? And 3 revolutions times 1, right? So the revolutions, they cancel out, right? So right here, we have 3 revolutions times over 17 revolutions. That's just going to cancel out, right? So it's going to be 3 over 34 years. But then we notice here that this is not the unit that we want, right? Why is it not the unit that we want? Anyone explain? Aiden, can you explain to me why that's not the unit that we want? This right here.
Because like uh
Right here. Right here. Can you see where it is? Or I did not mean to do that. Okay. Here. Yeah. So why is this the unit? Why is that unit incorrect?
because I don't know.
Aiden, what are we looking for? What are we looking for?
We're looking for the how many Earths passed? I mean Earth year passed.
How many Earth years passed? So if we simplify this down, right? So if we simplify this down, this unit is equivalent to 1 over years. Part I can't draw, but yeah, this is 1 over years, and that itself is a unit. That's the reciprocal of a year. But this is not how many Earth years have passed. This is how many 1 over Earth years have passed. So that's incorrect, right? Do you understand? So what we want to do is we want to flip it. We want to flip it so that the years is on top. Do we understand? This is kind of abstract. Do you understand, Aiden?
Yeah, I understand.
Yeah. So can you explain to me now why we don't want this unit?
It's because like it's like
Because
it's
the years is below. We want the years to be on top. Does that make sense?
yes.
All right. So why don't we want this? Why is this unit incorrect, Aiden?
Because it's supposed to be on top.
It's supposed to be on top. That's good because we want the Earth years to be on top. And if it's on the bottom, it's going to give us this unit. And I said, no, we don't want this unit. All right. So good. It's very good. Let me erase
Yeah,
this.
like we want the years on top.
We want the good unit on top. That's what we want. All right. So let's move on. Units are in 1 over years. So we flip it over. And it's going to be equal to 11.33 years. All right. So here's a good example. So we're going to use percentages now. All right, let me see how good we're time. We're just gonna do this this one, and then we're probably gonna end it. There's a lot of more stuff that I wanted to get over, but you can look over it in the notes that we're gonna release. So if approximately 7.71% of the Senate voted to approve a bill, and the Senate is made up of 144 people, how many people voted to approve the bill? So this is basically just a study on the percentages. We're going to skip over it just to better on time. Let me see. So unit conversions. So unit conversions are very important because we have units of all shapes and sizes. It's important in the real world to keep continuity in size by being able to use proportions to convert between units. So to convert between units, we utilize the same system of rates and ratios. So for example, in every 1 meter, there are 100 centimeters. And every 1 mile, there are 1.61 kilometers. And for every ton, there are 2,000 pounds, right? And we can go on and on. There are all these different types of units, right? So unit conversion. So for each of the SI units, each one of these units, so basically what that is that no matter if it's length, if it's time, if it's mass, if it's volume, they're all going to have these same system of prefixes, right? And symbols. So using this mnemonic, we can use this mnemonic to memorize the different prefixes, right? So if we remember, King Henry died by drinking chocolate milk. King Henry died by drinking chocolate milk. We can remember that the beginning of all of these are kilo, hecto, deca, base, deci, centi, and milli. So as you go up this, right, you're going to divide by 10. So for every kilogram, if you want to reach like 1/10 of that, 1/10 of a kilo is a hecto. 1/10 of a hecto is a deca. Do you guys understand? That makes sense?
Yes.
All right. I'm going to move on. So if the new section of a road is 5.5 kilometers long, then how long is it in centimeters? Well, so if 1 kilometer is 100 meters, and 1 meter is 100 centimeters, we can just set up this chain of proportions, right? So if we have 0.5 kilometers, we can set this up. Notice how this is a reciprocal, so this is on the bottom. We can cancel out these units, and in order to reach the 1,000 meters, right? So that's going to be that. And we multiply them, and it's going to be 500 meters, but it's not asking for meters, right? It's asking for centimeters, right? So we have 500 meters, and it's going to be, we want to cancel out the meters, and it's going to be times 100 centimeters, right? Because there's 100 centimeters in 1 meter. Notice how each one of these is the actual ratio here, right? Each one of these is this actual proportion, right? So 100 centimeters is in 1 meter. And we always have to manipulate that in order to achieve what we want. So this is going to be 5,000 centimeters because we did this chain of proportionality, right? You guys can look over the other ones. So in order to establish continuity, we must set up the ratios to multiply each other and to cancel out unwanted units. So here, kilometers, and there's another kilometer there. So we cancel these out, and we cancel these out. All right, we're going to keep on going. So complex conversions and applications. This is the last part, all right? All right. So last thing. So if not sure where to start, write down a given rate or proportion fraction, then determine what you are given and make a pathway to the desired ratio. So what this is saying, so this is basically just like a guideline to how to solve these questions. So write down the given rate or unit in the proportion fraction, and then you have to determine what you are given. So here, for example, we are given 55 miles per hour. And we have to determine the speed in meters per second, right? And so we're getting here that we have 3,600 seconds in an hour, and in each mile there's 1.61 kilometers. So we can set these up. and 1 kilometer in every 100 meters. So this is the dude, all right? So if we have here the ratio between the 55 miles per 1 hour, and you could go about this a lot of ways, but we're going to go first of all with the kilometers, right? So we're going to go with kilometers. We're going to want to cancel out the miles, all right? And so 161 kilometers times this amount. And so what this is going to do is going to cancel out here. Let me look at this annotation tool. Or yeah, so annotation tool. These are going to cancel out. But then these two, these are going to be tied, since this is going to be the new numerator, and this is the new denominator. And you can see that here, right? And so then whatever the product of these two is, that's going to be the new actual value. So it's going to be 88.55 kilometers over 1 hour, right? And that's all fine and dandy. And so here we go, 88.5 kilometers per hour, right? But that's not what we want. We want meters per second, right? And so here we have this, right? So we have 88.5 kilometers for 1 hour, and then we want to determine how many seconds that is. So we're gonna manipulate the denominator, right? So if there's 1 hour for every 3,600 seconds, then that means that we're gonna want to multiply them so that they cancel out. That gives 0.24583 kilometers per 1 second. So it's this amount of kilometers per second, right? And so we have this, set it up as a ratio, but then we have to multiply it because this is actually asking for meters per second, right? So we're gonna cancel these out. We're gonna set this ratio equal to this one. So I want you guys to notice that each one of these ratios, so this, and even this, they are all tying back to these ratios. These are given things that we need to utilize in order to determine our final product. So that's going to give you this. And then once you multiply these values, right, that's going to give you 583 meters per second. This is a doozy. I'm sorry, but I hope you guys are following along. All right, let's go back. So that's going to give you 24.58 meters per second. So we went from 55 miles per hour to 24.853 meters per second. All right, does that make sense, guys? How we utilize these things. All right. I hope this made sense. And yeah, that's gonna be the lesson.